The internet has survived viruses, cyber attacks, government espionage, and some of the largest data breaches in history. Billions of people trust it every day with their bank accounts, private messages, medical records, and state secrets. Entire economies depend on a fragile web of code and encryption that most people never think about. But somewhere inside, laboratories owned by governments, universities, and technology companies, scientists are racing toward a moment that cybersecurity experts have quietly feared for decades. A moment they call Q-Day. Not a war, not a blackout, not the collapse of the internet, something potentially far stranger. The day a quantum computer becomes powerful enough to crack the encryption protecting the digital world. And according to many experts, preparations for that day have already begun. Right now, every text message you send, every online purchase you make, and every password protecting your accounts relies on a simple assumption. The assumption is that certain mathematical problems are so difficult that even the most powerful computers on Earth cannot solve them in any reasonable amount of time. For decades, that assumption has held true. Take online banking, for example. Every time you log into your account, your device exchanges encrypted information with a server somewhere in the world. The same thing happens when you use a credit card, send an email, or store photos in the cloud. Hidden beneath the user-friendly interfaces is a layer of cryptography designed to keep your information safe. Most of modern encryption depends on problems that are easy to create but incredibly difficult to reverse. Imagine multiplying two enormous prime numbers together. For a normal computer, that task is relatively straightforward. But if someone hands you the final result and asks you to figure out the original prime numbers, the problem becomes vastly more difficult. This challenge forms the foundation of many encryption systems used across the internet today. The reason these systems work is simple. Classical computers are slow at solving those kinds of problems. In fact, they are so slow that cracking strong encryption by brute force could take millions or even billions of years. That enormous gap between what is possible and what is practical is what protects the digital world, or at least it used to, because quantum computers do not obey the same rules. To understand why cybersecurity experts are so concerned, you first need to understand just how different quantum computing really is. Traditional computers process information using bits. Every bit can exist in one of two states, 0 or 1. Every website, every photograph, every video game, and every artificial intelligence model ultimately runs on those simple building blocks. Quantum computers use something else entirely. They use qubits. Unlike ordinary bits, qubits can exist in multiple states simultaneously thanks to a strange phenomenon known as superposition. On top of that, qubits can become entangled, meaning that the state of one qubit can be linked to another in ways that seem almost impossible according to everyday intuition. The result is a machine fundamentally different from anything humanity has ever built. For years, quantum computers remained largely theoretical. Scientists could build tiny experimental systems, but scaling them into useful machines appeared almost impossible. The qubits were unstable. Errors accumulated rapidly. Many experts believed practical quantum computing was decades away. Then the breakthroughs started arriving. Governments increased funding. Major corporations launched dedicated quantum divisions. Research papers that once seemed purely academic began producing real hardware improvements. Google demonstrated experiments suggesting quantum advantage in specialized tasks. IBM unveiled increasingly powerful quantum processors. Microsoft pursued entirely new architectures designed to reduce errors. Startups around the world entered the race. Suddenly, a question that once belonged to science fiction became a serious topic of discussion among cybersecurity professionals. What happens if someone builds a quantum computer powerful enough to break modern encryption? That hypothetical moment acquired a name: Q-Day. The phrase sounds dramatic, but its meaning is surprisingly precise. Q-Day refers to the point at which a quantum computer becomes capable of defeating the cryptographic systems that secure much of the internet. Not every form of encryption would fail overnight. The reality is far more complicated than the headlines suggest. But certain widely used systems, particularly those based on factoring large numbers and solving related mathematical problems, could become vulnerable. And if that happens, the consequences could reach into almost every aspect of modern life. Banks could face unprecedented security challenges. Governments might need to rebuild classified communication systems. Corporations could discover that years of sensitive data are suddenly exposed. Hospitals, power grids, satellites, military networks, and cloud infrastructure could all require massive upgrades. The sheer scale of the transition is difficult to imagine, and yet, despite the enormous stakes, nobody knows exactly when Q-Day will arrive. Some researchers believe it remains decades away. Others think it could happen much sooner. The uncertainty is what makes the situation so unusual. For perhaps the first time in technological history, humanity is preparing for a threat without knowing whether it will emerge in 5 years, 20 years, or 50 years, and preparations are already underway. The reason experts are acting now has less to do with panic and more to do with mathematics. Replacing the cryptography that protects the internet is not something that can happen overnight. Modern encryption is embedded into countless devices and systems. Financial institutions, government agencies, communication networks, and industrial infrastructure rely on standards that took decades to establish. Changing them could take just as long. That is why organizations around the world have begun planning for what cybersecurity professionals call post-quantum cryptography. The goal is simple in theory, but enormously difficult in practice. Create encryption methods that remain secure even in a world with powerful quantum computers. In the United States, the National Institute of Standards and Technology, better known as NIST, has spent years evaluating new cryptographic algorithms designed to withstand quantum attacks. Researchers from around the world have submitted competing proposals, each attempting to solve one of the most important security challenges of the 21st century. The process has been slow and deliberate, because the stakes are extraordinary. Choosing the wrong standard could expose billions of people to risk. Choosing the right one could secure the digital world for decades to come. Meanwhile, intelligence agencies are paying close attention. There's a chilling phrase often repeated in cybersecurity circles: harvest now, decrypt later. The concept is simple. Imagine that an adversary intercepts encrypted data today. They cannot read it using current technology, so they store it. Years later, once sufficiently powerful quantum computers exist, they decrypt the information. Suddenly, secrets that were once considered safe become accessible. For ordinary social media posts, this may not matter. But for military communications, diplomatic negotiations, corporate intellectual property, medical records, and classified research, the implications are profound. Some information loses value quickly. Other information remains sensitive for decades. And that means the countdown to Q-Day may have already started. This possibility has transformed quantum computing into more than just a scientific competition. It has become a geopolitical race. The United States, China, the European Union, Japan, and several other nations are investing billions of dollars into quantum research. Governments increasingly view quantum technology not merely as an economic opportunity, but as a matter of national security. The nation that achieves practical quantum advantage first could gain significant influence in fields ranging from medicine and logistics to artificial intelligence and cybersecurity. That prospect has fueled both excitement and anxiety. Supporters of quantum research emphasize its enormous potential. Quantum computers could accelerate drug discovery by simulating complex molecules. They could optimize transportation networks, improve climate models, and unlock scientific breakthroughs that remain impossible today. The same technology capable of threatening encryption could also help solve some of humanity's most difficult problems. Critics worry about unintended consequences. They point out that history offers countless examples of transformative technologies producing unexpected disruptions. Nuclear physics gave rise to both clean energy and atomic weapons. The internet connected the world, but also created new forms of crime and misinformation. Quantum computing may follow a similar pattern. Extraordinary promise combined with extraordinary risk. And yet, despite the attention surrounding Q-Day, there is an important detail that often gets lost in sensational headlines. Quantum computers do not currently pose an immediate threat to your passwords. Today's quantum machines remain highly experimental. They are extraordinarily difficult to build and maintain. Most operate in specialized environments at temperatures colder than outer space. Error correction remains one of the field's greatest challenges. The quantum computers making headlines today are not secretly breaking into banks. At least, not yet. Building a machine capable of defeating modern encryption would require dramatic advances in both hardware and software. Experts disagree about how long that process will take. Some believe we are still decades away from practical quantum attacks. Others argue that recent progress suggests a shorter timeline. Nobody knows for certain. That uncertainty creates a strange paradox. If Q-Day is far away, investing billions in preparation could seem excessive. If Q-Day arrives sooner than expected, waiting could prove catastrophic. So governments and corporations are preparing for both possibilities. Banks are testing post-quantum security systems. Technology companies are experimenting with new encryption standards. Researchers continue searching for vulnerabilities and solutions. Quietly, almost invisibly, the foundations of the internet are beginning to change. Most people will never notice. The transition will not happen with dramatic headlines announcing the end of encryption. Websites will continue loading. Messages will continue arriving. Credit cards will continue working. Behind the scenes, however, one of the largest technological migrations in history may already be underway. And there is something strangely poetic about the entire situation. For decades, humanity built an interconnected digital civilization on top of mathematics. Now, another branch of mathematics threatens to reshape it. The very laws of quantum mechanics that puzzled scientists a century ago may soon redefine cybersecurity, economics, politics, and technology. The internet was built under one set of assumptions. Quantum computing is forcing humanity to reconsider them, and perhaps the The most remarkable part of the story is that Q-Day itself may not be a single day at all. There may be no alarms, no breaking news banners, no universally accepted moment when experts declare that the age of classical encryption has ended. Instead, the transition could unfold gradually. A breakthrough paper, a new processor, a leaked government report, an unexpected announcement from a technology company. Only in retrospect might people realize that the world crossed an invisible threshold. That is why cybersecurity experts are preparing now, not because they know exactly when Q-Day will arrive, but because they know that if they wait until it happens, it may already be too late. For centuries, humanity has relied on locks, walls, and physical barriers to protect valuable information. The digital age replaced those defenses with algorithms and cryptography. Now, quantum computing threatens to rewrite the rules once again. Whether Q-Day arrives in 5 years or 50, one thing is already certain. The race to secure the future has begun. And somewhere, inside laboratories, hidden behind security checkpoints and billions of dollars in research funding, scientists are working on machines that could change the internet forever. The terrifying part is not that those machines exist. It is that nobody knows exactly when they will become powerful enough to matter. If you enjoyed this video and want to explore the technologies quietly reshaping our future, subscribe and join us for the next story.